Assalamu alaikum everyone. So our today's lecture is about how to solve linear differential equations. So the title of this video would be solving linear differential equations. So we know what are linear differential equations, right? So linear differential equations are equations where the unknown would have the highest degree of 1. Okay. So linear equations with constant coefficients are particularly easy to solve, and it is a bit more difficult to solve the variable coefficient ones. So a linear coefficient equation, linear differential equation with constant coefficient might have this format. So you might wonder that integrating both sides of the equation with respect to t might give us the solution, but it actually doesn't, because we have, if we integrate both sides of the equation with respect to t, then we have this. Let's say there are dt in both of the sides, so we have yt equals to a, then yt dt plus bt plus c, and as y is the unknown here, we cannot actually integrate y because there is no primitive for y. So in this way, simply integrating both sides of the equation actually does not give you a solution for linear differential equations. So there is a precise formula for solving linear equations with constant coefficients, but I would not tell you the formula. Rather, I would derive the formula from the original equation, so that you get a clear idea how to solve linear differential equations. Okay, so a linear differential equation with constant coefficient has this format: y prime equals to ay plus b. This is the generalized format. So let's solve. So the first step, so in this step, or in the first step, let's say b is equals to 0. So in the first consider this case where b equals to 0, then we have y prime equals to ay. Now we need to solve this equation for y. So we can write this equation as y prime divided by y equals to a. Then if we integrate both sides, we get this. So you know, for the formula for this sort of derivatives, or this sort of values, where in the numerator we have the derivative of the denominator. So if you integrate the left hand side, you would get something like ln of y, something like this, and we have at plus c naught. C naught is an integrating constant here, and t is the independent variable, so that's why this is t. So okay, so let's say there are dt dt. Yeah, so now you have mod of y equals to e to the power at plus c naught, or you can say that this is y equals to plus minus e to the power at plus c naught. So we can say that y equals to say that this is basically e to the power c naught and e to the power at. Let's say plus minus e to the power c naught. So this is, as this is a constant, c naught is a constant, so e to the power c naught is also another constant. Let's say this constant is c, so we can say that y equals to c e to the power a t in this case. So this is the solution. So this y can have many solutions based on the value of c. So for different values of c, you will get different y, and so we can guess that there might be infinite number of solutions for this unknown. Okay. Now the second step. So in the second step, b is not equals to 0. So okay. Sorry. Yeah, in the second step, b is not equals to 0. That means we have y prime equals to ay plus b, right? So let's rewrite this equation in this format. Y prime equals to a, take a as a common factor, so we have b by a, right? And let's rewrite the left hand side similar to the right hand side. So we can write y plus b by a whole prime equals to a into y plus b by a. So this is completely legal because y plus b by a, if you find the derivative of this particular term, you would see that this is basically y prime, because derivative of b by a, because derivative of b by a is equals to 0. So that's why this is legal. Yeah. Now let's assume that so there are two similar terms in two sides of the equations, this one and this one. Let's say this one is this particular or let's say this is z. Okay, let's say this is z. So we have z equals to a, z prime equals to az. So we have z prime divided by z equals to a, right? So yeah, so now we can solve this particular equation similarly like the like from this one, this particular equation. So we have with following the similar approach. All right, so we have z prime divided by z dt a dt. So sorry, so we have ln of z equals to at plus c naught. Then we have z equals to plus minus e to the power at plus c naught. Then similarly we can write it as z equals to c e to the power at, similar to this approach. Now z had the value of y plus b by a equals to c e to the power a by t. So we have y equals to c e to the power a by t minus b by a. So this is the solution for y. And as you can see, y can have infinite number of solutions in this case as well, because c is a constant, and for different values of c there might be different solutions for y. Okay, so we have this general equation, general solution for linear differential equations with constant coefficients. So let's see an example that how is it solved, how it's solved. So let's say we have y prime equals to 2y plus 3. So let's solve it from the scratch. Let's not just use the equation here or the solution here. So we have y prime equals to 2y plus 3 by 2, then y plus 3 by 2 whole prime equals to 2y plus 3 by 2. We wrote this following this particular approach. Now we have, let us say this is z, so z prime equals to 2z. So we have z prime divided by z equals to 2. So let's integrate both parts. So z prime divided by z equals to integration of 2. So we have yeah, sorry. We have ln of z equals to 2t plus c naught. So if z equals to plus minus e to the power 2t plus c naught, so we have z equals to c e to the power 2t, and rewriting the z term with its original value, we have y plus 3 by 2 equals to c e to the power 2t. So we have y equals to c e to the power 2t minus 3 by 2, where c can have any real value. So this is the solution for this particular differential equation. So I hope you get this part. Now this particular method is actually very good when you solve differential equations with constant coefficients, right? But it gets particularly difficult in cases of linear differential equations with variable coefficients. However, there is a way to solve linear equations with both constant and variable coefficients, and that particular method is named as the integrating factor method, right? So how to utilize that particular method? Let's see. Okay. Okay, so we have the integrating factor method. So let's say we have this particular equation ay plus b. So we can write this as y prime minus ay plus equals to b, right? So in integrating factor method, after this step you have to multiply both sides of the equation by the integrating factor. Okay, let's say the integrating factor is the Greek letter mu, okay, and this is equation number 1. So multiplying equation 1 by mu, we have mu y prime minus a mu y equals to mu b. Now what is the definition of mu? So the definition of mu is we choose a positive function mu. So mu is chosen in a way such that minus a mu equals to mu prime. So this is the definition of mu. So we'll definitely see an example, but this is the formal definition of mu. Okay, let's say this is equation 2. So if we rewrite the value of mu prime in this equation, let's say this is 3. So from 2 and 3 we can write that from 2 and 3 we can write that mu y prime plus mu prime y equals to mu b. So we basically replaced the minus a mu by this mu prime. So in the left hand side you can see that this is basically a total derivative of the product of these two functions. So this can be written as mu y whole prime equals to mu b. So this is the associative law of the derivatives. Okay. Now we have to work with the integrating factor function here. So we had, so from 2 we know that mu prime equals to minus a mu, minus a mu. So this can also be written as mu prime divided by mu equals to minus a, So if we solve this for mu in the previous manner, we can write this as, so we have to solve it for mu. So let's integrate both part of the equation. So this can be written as, the similar solution. So mu would have something like plus minus e to the power c naught into e to the power minus at, as the constant a has a negative sign here. So this, let's take this, so as this is not the total solution of the, or the final solution of the given equation, let's say this particular constant is c1. So mu equals to c1 e to the power minus at. And for integrating factor, see, for this integrating factor, c naught is assumed as 0. All right. So this whole C1 becomes actually plus minus e to the power c naught, so plus minus e to the power 0, so it's 1. So this mu becomes e to the power minus at. Alright. Now if we plug in this value of e to the power minus at here, what would we get? So let's erase the upper part. So we have e to the power minus at y whole prime equals to e to the power minus at b. Okay, we have this. So now we have to solve for y. So the right hand side here, e to the power minus at y whole prime equals to the right hand side. I want to modify this right hand side to something else. So this right hand side can be written as minus b by a e to the power minus at whole prime. Okay. Why did I do that? Because I want to take the right hand side at the left hand side, so that I can write the whole differential equation as a total derivative. How? I will explain it later. But if you inspect that if this representation is true or not, then you can see that differentials of minus b by a e to the power minus a by t is basically this one. So solve this and you will get this b e to the power minus a t, right. So now what you can do, you can take the right hand side in left hand side, so or bring the right hand side into left hand side. So we have this, and we can write it like this one equals to 0, because we have brought the right hand side in left hand side. Yeah. Now we have another common thing, e to the power minus at. So this can also be written as y plus b by a e to the power minus at whole prime equals to 0. So as you can see, the whole differential equation the whole differential equation is this. So by doing the integrating factor method, we have transformed the whole differential equation as a total derivative. So now if you if you integrate both part of the equation, you have a very easy differential, or if you have a very easy integral at the right hand side, right, because this would only be t at the this would only be constant at the right hand side. So this particular representation of writing the whole differential equation as a total derivative is known as the potential function. Okay, so the potential function is written as like this. I think this is shy or something like that. I think the so this is a Greek letter, chi or shy. I forgot the pronunciation actually. Let's call this as shy. Okay, so this is psi of ty equals to y plus b by a e to the power minus at. So this is the potential function because it potentially holds the solution for the unknown. Okay, so this is known as the potential function. So the formal definition of the potential function is when this whole differential equation is written as a total derivative, then this particular term would call as a potential function because it potentially holds the solution for the unknown. And what is the informal definition of potential function? So whenever you are applying the integrating factor method or any other method, and you represent the whole differential equation as a derivative making the right hand side 0, then that particular left hand side would be called as a potential function. Okay, so I hope this is clear. Now if you integrate both part of the equation, you would see that you have, so this is nothing but 0 into t, right? So we have, so if you integrate both part of the equation, integrate psi of ty equals to integration of 0 into t, then we have psi of ty equals to c, right? And the potential function is basically y plus b by a e to the power minus at equals to c. So if you multiply both sides of the equation by e to the power at, then we have, sorry, made a mistake. Yep. So we have y plus b by a equals to c e to the power at. So we have y equals to c e to the power at minus b by a. So this is the solution, and c might have any value from the real number. So this is the solution, and this is also a theorem. Okay, this is also a theorem. So you might the theorem is for integrating factor method. So for integrating factor method, for linear differential equations, for any b and a, the solution would be this. And you might say that this integrating factor method is a longer approach than the previous one, but it can solve any sort of linear equations with either with constant coefficient or variable coefficients. Okay, so this is very useful. So let's see an example of how to solve the linear differential equations with the integrating factor method. Okay, so let's say you are given this equation y prime equals to, let's say, 3y minus 5. So this equation can be written as y prime minus 3y equals to 5. So in this equation, from the previous derivation, we saw that the integrating factor mu is basically e to the power minus at. So in this case, the as I said, that the previous derivation was basically a theorem. So you can use the theorem to solve this problem. So we have, or we can derive it from the very beginning. It's your choice, but you can use the theorem. So e to the power minus so this has roughly the representation of y prime equals to ay plus b. So here a has the value of 3 and b has the value of -5. So so in this case, the integrating factor would be e to the power minus 3t. Okay. So multiplying both sides of the equation by this so multiplying both sides of 1 by the mu, we get that it should be mu y prime minus 3 mu y equals to 5 mu. So we have e to the power minus 3t y prime minus 3 e to the power minus 3t, then y equals to 5 e to the power minus 3t. So as you can see, it should be e to the power minus 3t, 3t y prime minus e to the power minus 3t whole prime y equals to 5 e to the power minus 3t. So we can write this as e to the power minus 3t y whole prime equals to 5 e to the power minus 3t, right? So like the previous approach, we can solve the following lines here for this particular equation. Let's say this equation is 2. So so we have so we can rewrite this equation as e to the power minus 3t y whole prime equals to, so this 5 e to the power minus 3t, so this can also be written as minus 5 by 3 e to the power minus 3t whole prime. So this can be written as minus 5 by 3 e to the power minus 3t whole prime, and we convert this into the potential function. So this can be rewritten as this. So the later part is much easier. So now we have, so after all the integration, let's do it in shortcut. So there might be lines here. So what I would do is that I would write this as e to the power minus 3t y plus 5 by 3 e to the power minus 3t equals to c. So y would be something like c e to the power 3t minus 5 by 3. So I hope I'm not wrong. So this is the solution for the given equation. So for different values of C, it might have different solutions. Okay. So if I draw a graph, it would take a picture like this. So for let's say this is y, this is y prime, this is t prime, and this is t. Okay, and this is t equals to 0, y equals to 0, let's say. So for c equals to 0, we'll have this solution. So let's draw the solution lines with a different color, let's say green color. So this would be the solution, minus 5 by 3 for c equals to 0. If you put c equals to 0 here, then you will get y equals to negative 5 by 3. So this is the solution for y in case of c equals to 0, and you will get this solution or this sort of solutions for c greater than 0, and you will have curves bending below the negative 5 by 3 for c less than 0. So these are few representations of this particular solution with different values of c. Okay. So I think this is enough. So I will show you some more examples during the discussion class, but so these are two approaches that we have solved, and the later approach, the integrating factor method, is widely used for solving linear differential equations with constant or variable coefficients. Okay, so we might solve equations with variable coefficients in the class. Okay, so thank you, and I would see you guys in the next class, inshallah. Assalamu alaikum.